Welcome back to another day of calculus. Today, what I want to talk about, we've just looked at fundamental theorem of calculus, part 1 and part 2. And I think that it's a good idea to pause and do some examples, do some applications, some of which we've already seen. But brief review. So what is fundamental theorem of calculus? The way people state it is you can compute an integral, signed area under the curve, by looking at evaluating an antiderivative on the endpoints. So what is capital F of x? Its derivative has to be equal to little f of x, and little f of x should at least be piecewise continuous. You can even weaken that a little bit more, but that's not the point of this class. And the other part of it says that if you take the derivative of an integral going from a constant to the variable now, f of t dt, that's going to be nothing but f of x. So those are like the two parts of the fundamental theorem of calculus. But if you go back to where this was originally motivated from, like you have something like maybe s of t, like linear motion, so s of t was position, s prime of t was velocity. And then on some time interval, maybe from t0 to t1, you have something like, we define these physical quantities like displacement. You've heard me mention, which is literally defined to be where you end up minus where you started from, at least for linear motion in a straight line. So taking into account that your velocity function from t0 to t1, maybe it's positive for a while, and maybe you slow down and even start going into the opposite direction. And then your displacement is actually equal to the integral over that same interval of your velocity. So that's like an example of where the fundamental theorem of calculus actually came from, from some of these physical things. You could also look at your total distance traveled, not just forward, but also backwards. And wouldn't that be something like, instead of area under the curve minus area over the curve, if you want to look at your total distance traveled, you would actually want to add these up together instead of subtracting them. And one way to do that is just integrate the absolute value of your velocity. Absolute value just makes the function positive. So if you're saying, well, like, what would my displacement be if I were traveling in the forward direction the whole time instead of traveling backwards here? Add that up, that gives you your total distance traveled, which actually doesn't have a great, easy formula, but at least you can still do it with an integral. So generally speaking, in physical applications, I mean, it doesn't doesn't just have to be distance and velocity. Like there's lots of other applications, but the way this generalizes is this expression on the left-hand side. People call that the net change. Like the net change in your position is certainly where you ended up minus where you started. And so the net change is the integral of the rate of change. So, I mean, that's kind of how you would state fundamental theorem of calculus, part 1, as an English sentence, that the net change of a function is the integral of the rate of change. And so if that integral, if that rate of change was constant, then this is just nothing but a statement like distance is velocity times time, or something like that. But the idea behind calculus is that when that rate of change itself is variable, then you approximate it, with the rectangles, you create the integral, and then you have this quite beautiful theorem using mean value theorem that tells you this net change of the quantity is actually equal to the integral of the rate of change of that quantity. The reason why this is useful in physics and in life is because things that are rates of change, those are things that are easy to measure. Like if you're in your car, it's easy to measure your velocity at the current time. But things like net change over a larger time interval, those things are more difficult to measure. So that's why a theorem like this is really good, because you take the thing that's easy to measure, you integrate it, and you are given more information. You're given the information it's difficult to measure. So let's give you an example to work on. So let's give you an example that lets you use this collection of formulas. So what I'd like to practice with. So say that a particle in linear motion has velocity given by v equals t cubed minus 10 t squared plus 24 times t meters per second. And so please compute the displacement over the time interval from 0 to 6 seconds. And please compute that total distance. On the same time interval from 0 to 6 seconds. So give that a try for a couple minutes, and then we'll discuss it. Okay, so let's do a little bit of discussion. So if you want to find the displacement, I guess I just erased the formula, but that's going to be the integral from a to b. So here a equals 0 and b equals 6. So you're taking the integral from 0 to 6 of the velocity function. So t cubed minus 10t squared plus 24t. So we're using the general principle that the net change, that is to say the displacement, net change in position, the displacement, is equal to the integral of the rate of change, which in this case is the velocity. And so to compute this, you find an antiderivative. So t to the 4th over 4 minus 10/3 t cubed plus 12t squared. So find an antiderivative and then evaluate it from 0 to 6. And evaluating at 0 will just give you 0. Here you get 6 to the 4th over 4 minus 10/3, 6 cubed plus 12 times 36. So 12 times 6 squared. Yeah, there's various ways you can calculate this. I think putting it into a calculator is just fine. I solved it on Desmos while we were messing around, so I found that the answer was 36. And what are the units? They're meters. So you should include the units when it's a physical problem. So if your velocity is given in meters per second, your position would correspondingly be in meters. It's interesting to keep track of how the units change when you differentiate or integrate. The position function would be like in, people use these brackets to indicate the units. The position function would be in meters, and the velocity is a derivative of position. So when you're doing derivative, you're taking a limit of a difference quotient, which is like dividing by time. So the units, when you take a derivative, always give you an extra factor of whatever you're differentiating against on the bottom. So with derivative with respect to time, it goes from meters to meters over seconds. Then when you integrate, integrating actually inverts the operation of differentiation in a way. So integrating removes that unit and brings it back to meters. So you integrate a rate of change and get not a rate of change in response, but you get like an actual a net change of the original unit in response. Now, if you want to do total distance, then you're going to be integrating the absolute value of velocity. And in order to do that, there's really only one way to reasonably do that. And you need to understand where this function is positive and where it's negative on the interval from 0 to 6, which for polynomial just means finding the roots. And I don't know if I'll spend too much time trying to find the roots of the polynomial, but you'll note, of course, that you can factor out the t immediately. So this is like t times t squared minus 10t plus 24. And we'll see if the question author has been nice to us. Like maybe we can factor this over the integers. We would need two numbers that multiply to 24 and add up to negative 10. So what does that? I mean, like negative 12 and 2 would do it, but that's negative 24. What else would do it? 4 and 6. So like negative 4, negative 6. So the roots of this velocity polynomial are t equals 0, t equals 4, and t equals 6. And 0 and 6 are at the boundary of our interval. So those are, two places where we're 0. And it looks like we're crossing also at t equals 4. So what I want to do is I want to write this integral of v dt as like integral from 0 to 4 of something plus integral from 4 to 6 of something. And I need to figure out whether v is, so like, I guess I really want to integrate the absolute value of v. And so if I break it up, it's either going to be positive or negative here. It's either going to be positive or negative there. So like, which is it? You might test a point. If I plug in t equal to 1, I'm going to get positive, negative, negative. So it looks like I have to be positive from 0 to 4. So I could integrate v, and I've got a root at t equals 4. Am I positive or negative from 4 to 6? Well, if I plug in maybe 5, positive, positive, negative, it looks like I'm negative here. So the absolute value would be the negative of v. So that's what you would do. So now you've got like 2 more integrals to calculate, but you've still got the same antiderivative. So I won't do both of them, but I'll show you this one, right? So you would do integral from 0 to 4 of v of t is now, well, you've already got that antiderivative. So you can continue to use it. But just go from 0 to 4 and then calculate out like whatever the answer is. And I'll do the other one from 4. I'll write down what it is and maybe not do the calculation. This time you're integrating the negative, which, since you've already got the antiderivative for v, like you can use linearity of the integral. Just rewrite this as the negative of integral from 4 to 6 of v, which is now going to be the negative of, take your antiderivative from 4 to 6. So plug in 6, subtract plugging in 4, then put a negative sign in front of it, and add that to your answer here. So add those two together, and I'll refer to the book. So on 0 to 4, we get 128 over 3. And from 4 to 6, integrating the negative, remember, we'll get negative 20 over 3. So this integral from 4 to 6 is negative 20 over 3, and then subtracting that gives us 20 over 3. So 148 over 3 meters would be your total distance traveled compared to your shorter displacement. So are there any questions or comments on how I'm calculating that? I want to show you a visualization just because let's take advantage of being online, and visualizations are cool. All of you are in a unique and wonderful position where these days you can just go on Desmos and like check all your work and see if it kind of makes sense. So what I've done here is I've graphed this function, and I used x instead of t on Desmos, like whatever. So x cubed minus 10x squared plus 24x, and then you can see it here. So this is the velocity function. And you can see it's got 3 roots, just like was promised, at 0, at 6, and also over at 4. And we figured out by testing one point that it had to be positive from 0 to 4, and look, that's totally right. We figured out by plugging in 5 into the factorization that it should be negative from 4 to 6, and look, that's totally right. So when you integrate from 0 to 6, when you calculate the displacement, what you're doing is you're calculating the red area and subtracting from that the blue area. And you can see what I've done is I made this function capital F of x, which is the antiderivative. This happens to be equal to the, x to the 4th over 4 minus 10x cubed over 3 plus 12x squared plus or minus a constant. But we learned last class period that another way to write antiderivatives is just, integrate from constant to variable. And I've got a set to 0 and b set to 6. So this actually is that antiderivative that I wrote down. It's not just plus a constant. It really is x to the 4th over 4 minus 10x cubed over 3 plus 12x squared. And then when you plug in like x equals 6 to that, you end up, of course, with the definite integral from 0 to 6. And so I've set b equal to 6 in this worksheet. I've got it set up so you can like change everything to do different problems. And you can see the answer that pops out is 36, just as expected. So the red area minus the blue area is equal to 36. And I mean, if you're worried about academic honesty or something, I wouldn't worry about that at all. I think it's really cool to be able to do this. Like, of course, when you're writing down your solutions, you would have to know how to actually find the antiderivative and how to do calculations and show them. Showing your work and communicating is a fundamental part of the process of being a human, but also being a scientist. So of course you would show your work on your homework, but you can use this to validate yourself and to figure out what's going on. And to do the other one, I mean, this does show you that you would have to integrate from 0 to 4 and then also find the integral from 4 to 6. So like if you did b equal to 4, that gives you 42 and 2/3. That's 128 over 3. And if you did like a equals 4 and b equals 6, so it's really cool. You could just like slide this around, and the answer is negative 6 and 2/3. So that's negative 20 over 3rd. And it's negative because it's the negative of the area, but this is the thing that you would subtract when you're integrating the absolute value to give you 128/3 plus 20/3. And it really does work out to 148 over 3. So like it takes a little bit of time and effort, but it's actually really cool. And we would have no hope of doing this just from the definition of the integral We really need to be able to compute integrals with any derivatives in order to do this efficiently. Well, I shouldn't say no hope. I think that like we could do it. It would just take a lot more work without using the fundamental theorem of calculus. So I hope you like that physics demonstration. We'll go back to this business of marginal cost. And I mention this in case you ever see an economics class. They like to talk about this stuff. So you're running a business or whatever, you're producing an item. Remember, you have this cost function, C of x, which is like cost to produce x units, and then you have the derivative is what you call the marginal cost. And if you are producing huge numbers of units, like if you're producing like 200 million iPhones or something, then the marginal cost, like at some point, x naught, is reasonably well interpreted as the cost to produce one more unit. And I won't go over the explanation again about like why that's true, but go back and watch that video or review the section in the book. And so you've got the cost function. The derivative is the marginal cost, which roughly speaking is the cost to produce one more unit. And then you can turn that around. If you know your marginal costs at each stage, you can integrate that to give you cost function of b minus cost function of a. And so like what does that mean? That's like the cost to increase production from A to B. So like if, going back to iPhones or whatever, if you knew your marginal cost and you were currently producing like 300,000 units, you could, just by knowing your marginal cost, you could then estimate how much it would cost you to increase production by 100,000 units. The idea being that your marginal cost will change. It will depend upon how many units you're producing. So you would actually want to compute an integral to get net change as an integral of rate of change. And it's just another application. Like it's the same principle, but it just has a different feeling because not everything is velocity or displacement, but you'll see lots and lots of different names that all have this relationship, that all fall under the category of net change as an integral of the rate of change. And then you get, all these word problems. They'll be phrased in different ways, but they all boil down to setting up the integral and then computing it. And so I'll briefly touch on this word problem from the text, at least show you how to set it up. So let's say the marginal cost of producing X computer chips in units of 1,000 is given by this polynomial. I don't know how realistic it is to assume that cost functions are estimated by polynomials. I've never worked like with a big business or anything, but but whatever, that's the setup that we're given. So find the cost of increasing production from 10,000 to 15. So cost to increase from 10,000 to 15,000. And second part, to determine the total cost of producing 15,000 chips, assuming it costs $30,000 to set up the manufacturing run. So in other words, if C of 0 equals 30,000, then find the total cost to produce 15,000 chips. So this is certainly, like, it's going to go easier when I'm explaining it, but when you're seeing this on an exam or on a test or whatever, you're just given the word problem. You're not given, you're not given this formula and the explanation along with it. So you do have to think to yourself, like, how am I going to set this up? But you're given a lot of hints and clues because you're given that you've got a marginal cost, which you know is a derivative, and you've got a formula for it. And so if you want to increase production from 10,000 to 15,000, I would interpret that in terms of the cost function, right? So and how can we do that? So first, we're told that x is in thousands. So 10,000 would be x equals 10, and 15,000 would be x equals 15. So we don't want to get tripped up by that. And of course, since I've already written it here on the other side of the board, right, cost to increase production from A to B, that should be the cost of making 15,000 chips minus the cost of making 10,000 chips. That's right, that's reasonably what it means to increase production from one level to another. So what you're being asked is, what is C of 15 minus C of 10? And then in order to do that, you'll know that's the integral from 10 to 15 of C prime, which is 300x squared minus 4,000x plus 40,000. And I'll leave it to you to actually integrate out the polynomial. You just find an antiderivative and then evaluate it from 15 to 10. I will write down the final answer for you, though. It's $187,500. And so make sure to include units, of course, whenever you've got a physical situation. Are there any questions or comments on that? So all of these problems, every single one of them, they're all going to go back to, writing down in words. Can you calculate a net change by integrating a rate of change? And typically in every single setup, it's the rate of change that you're able to measure. It's the net change that you're wanting to calculate. So what about the second part? So if it costs $30,000 to set up the manufacturing run, so that the cost to produce nothing would be $30,000, if you set up the manufacturing run and didn't make anything. So can you find the cost to make 15,000 chips? This one's a little more difficult if you've never seen it before. But actually, I would do the following. I would go back to this principle that like net change is equal to the integral of rate of change. And I'm interested in finding out C of 15. So C of 15 is the cost to make 15,000 chips. I don't know what that is, but I do know that C of 15 minus C of 0 is equal to the integral from 0 to 15 of this marginal cost function. That's the idea. So you're using the fact that the net change C of 15 minus C of 0 is equal to that integral. So you use the same antiderivative, you calculate it out once again. And the answer is 487,500. I'm trying to skip some more of the routine calculations so we can do more problems. And why does this help you? Because now you can just solve for C of 15. So you know that C of 0 is equal to 30,000. So that's telling you now that C of 15, the cost to produce 15,000 chips, is actually $487,000. 500 plus C of 0, which was given to us as being 30,000. You would add those two numbers together to get your final result, which is 517,500. Any questions or comments on that setup? The book is kind of biased towards physics and economics in its presentation. Can we find a problem involving medicine? I want to do one that like relates to medicine somehow. I'm in section 5.7. We could do number 26, although it's got a pen and paper symbol next to it, so. But whatever, let's give it a look. So if you've got your book, you can turn to page 338 and look at problem 26 with me, but here's the statement. So cardiac output is the rate, R, of volume of blood pumped by the heart per unit time. So cardiac output is a rate of change, blood pumped per unit time, liters per minute. Let's make a little setup here. So our liters per minute cardiac output. Doctors measure this by injecting A milligrams of dye into a vein leading into the heart at T equals 0. So inject dye in the amount of A milligrams. And recording the concentration of dye in milligrams per liter pumped out at short regular time intervals. So milligrams per liter pumped out at regular time intervals. And there's a little figure where, they just say you're injecting the dye before it gets to the heart, and then you're measuring the concentration after it is pumped out of the heart. And so you get these little charts where you've got the concentration on the y-axis and you've got time on the x-axis. So part A says explain the quantity of dye pumped out in a small time interval from t to t plus delta t is approximately given by some formula. So part A says explain the quantity of dye pumped out in a small time interval from t to t plus delta t is roughly equal to R times C of t times delta t. See if you can put all that together for a minute, and then I'll come back and discuss too. And that's supposed to be the dye pumped out in this time interval. Okay, after letting us all think for a minute, so I'm confronting this problem for the same time, just as you. I like to check the units first of everything, so I use these square brackets for units. Remember, this was the rate of cardiac output in liters per minute, so that's liters is a measure of well, I'll just say liters per minute. The units of the concentration were milligrams per liter, and of course the units of time are in minutes. So if you multiply all these together, liters per minute times milligram per liter. So these two give you, well, the liters would cancel and you're left with milligrams per minute. So milligrams per minute times a small number of minutes would absolutely give you something in milligrams, which makes sense for dye being pumped out. That should be in milligrams. So that makes sense to me. And so why R times C of T? Because that's the rate we're pumping out, and C of T is the concentration. So it makes sense that the amount per minute that you're pumping out should be your rate times your concentration. And then the total amount of dye pumped out would be that rate times the amount of time that you are pumping something out. So part A is just explaining it, and so that's my explanation in words. You would write something down. Part B says something like, show that A is equal to R times the integral from 0 to t, C of t dt, where capital T is large enough that all of the dye is pumped through the heart, but not so large that the dye returns by recirculation. So the amount of dye that you inject, I mean, basically what's happening here is like, you've got this setup where you're putting in this amount of dye to the heart, and then you're measuring it as it gets pumped out. So like the amount that goes in has to be equal to the amount that goes out. That's the assumptions that are on T that are being made. So this is the amount that goes in, clearly. So why is this the amount that goes out? What should this integral from 0 to t of the concentration be? I mean, it's an amount in milligrams, right? So because it's not quite right. So the unit, sorry, let me back up. So what does integration do? So what I explained before was when you're integrating something, it takes whatever units you have and multiplies them by like time. So the integral of velocity would have units of velocity times time, which would be distance. If you have units of milligrams per liter and you're integrating that over time, like the new units here would be milligrams per liter times time. And that should check out where, like, if we multiply this by liters per minute, then liters cancel on the bottom and minutes cancel on top, and you are left with milligrams. This is called dimensional analysis. You want to check, first of all, that your units on the left-hand side make sense with the units on the right-hand side. And oftentimes that's like really helpful for doing your problem. So this is like the area under the curve, right? So it's your how do you interpret this physically? How do you interpret the integral of a concentration physically? We're out of time, so I think I'll let you work on that. This is kind of a cool exercise, so I'll let you work on that, and let's see what you come up with. Let's make that a homework problem. Let's have you do page 338, number 26 for homework. I'll put that up on the classroom. And then I'll do it too, and we'll come back and discuss at the beginning of class on Monday. Then there'll just be like one more section to do, substitution methods, and then we'll do review on Wednesday. And then unfortunately, the final exam comes really fast after that. So final exam would be next Friday. So that'll be the plan for the whole course. So any final questions or comments? Okay, so I'll see you all on Monday. Take care.
Thank you.